It's great to be here. Hi, everyone. Thanks for coming. Today, I'm going to talk about embedding-based classifiers for large output spaces. Before I start, I should mention that this was a joint effort with a bunch of great collaborators from Google Research. I would like to tell their name right now. So Xuan Guo, Xiang Wang, Dan Holtman, Sashang Reddy, Satyan Kale, and Sanjeev Kumar. And the results that I'm going to present today will be also presented in NeurIPS 2019 in December in Vancouver, BC. So I would like to begin by describing what I mean by large output spaces. Okay? So suppose that I search for Google I/O 2019 in YouTube. And you can see in this page that the keynote talk by Sundar is being played. Okay? But at the same time, we have this autoplay section in YouTube that once this video is finished, it decides automatically which video should be played at the next level. So here, for example, you can see that Google I/O 2019 highlights has been chosen. Okay, but basically the question for us here is that how should YouTube choose the next video to show to the customer that is watching this video right now? First of all, let's see how many possibilities we have in here. So if we search Google I/O 2019 YouTube and Google search, you can see that, OK, here are the top 3 results. The first result is like Google I/O 2019 all sessions in YouTube. Second result is Google Keynote that we were watching together. And then the third result is Google I/O 2019 highlights. That was the next video as I showed in here. That was going to be played after this automatically. OK, but the question is that how many possibilities are there? So according to the Google search, you can see that there are almost 25 million results. OK, and then the highlights video was chosen among almost these 25 million results. And the question right now is that, OK, what is the best algorithm? How can we come up with a good algorithm to solve this problem as a classification problem? Okay? So how does it differ from traditional classification problems? So I give you 2 examples. Let's say we want to do image recognition. One is this classical MNIST dataset. You might have heard about it, which the goal of this problem is to recognize the handwritten digits. And we have 10 classes, 0 to 9. OK, and the other class is this CFAR10 data sets that we have, that the goal is also to do some sort of like image classification, but the number of classes is also like 100 classes. So these are traditional classification problems. The number of classes are very small. But on the other hand, when we search Google I/O 2019, you can see that there are 25 million possibilities, 25 million classes that we can choose from. OK, and this is what I mean by having a large output space, basically. So pretty much different from traditional classification. So there are, in general, 3 different methods for solving this large output space classification problem. And I would like to briefly mention 2 methods and focus on the third one, which our work is mostly related to as well. So one method is the tree-based. Basically, it's called like a tree-based method that you have a hierarchical structure over these many number of labels. The other approach is called sparse linear methods or one versus all methods. That because you have a large model, because you have like tons of labels in here, you will have a large model. So if you force your model to be a sparse, you can make it computationally efficient, basically. OK, and that's a famous method as well. So I just want to mention this point that classical approaches such as logistic regression or support vector machine is not going to work in this problem because the model is going to be so huge that it's going to be computationally infeasible. OK, so the third method that I'm going to also talk about it more today is called embedding-based method. And what do I mean by embedding-based method? How many people have heard about embedding in here? OK, great. So suppose that we have an input query, Google I/O 2019. OK, so we can code this input query to some mathematical vector. Let's say that I denote it by x in RD. OK, so how do we do this? There are different techniques to do that. So one simple way is called one-hot encoding. That for each word in the dictionary, we have one vector which corresponds to 1 in that specific entry corresponding to that word and 0 otherwise. So in that way, we can encode every query to a mathematical vector. So for every input query, we have this input vector, okay? And then we can have a function, which we call it an embedding function, then that can take this input vector in here, and then the output of this function would be a vector which is in another space. Okay, so the input vector is in RD. It's a like capital D dimensional space of real numbers. And this output vector is in small d dimensional space of real numbers. Okay, so we call this output vector an embedded vector. And then we call this function an embedding function. Okay, so once we have this embedded vector, we can give it to a classifier. Okay, so what happens is that we have this embedded vector that we got it from our embedding function. We give it to this classifier, which receives a vector in small d dimensional space of real numbers, and output a binary vector, which is a k dimensional vector, but it's binary. It's just like 0 or 1. So if we have k labels, k different labels that could be, let's say, 25 million labels. So we have a vector of size 25 million that each entry is either 0 or 1. So it's 0 when that label is not in that entry, or it's 1 when that label is that it corresponds to that input, or is that that label is basically in that entry. Okay, so this is our classifier, and then our output label vector. You can see that it's a binary vector that we can show it by f of phi of x. So phi of x is our embedding function, and f is our classifier. And the whole point of an embedding-based method is basically designing this embedding function and designing this classifier in here. Okay? Any question? Sure.
Is R small d a linear dimension reduction type process?
It could be linear or nonlinear. I will go over it in the future. Yeah. Okay. Okay, so I briefly talked about the previous methods, tree-based methods, sparse methods, and then also I mentioned that this work is about an embedding-based method. One widespread belief prior to this work in the research community was that embedding-based methods are not good for classification in large output space, because when we embed an input, we are compressing the input a lot. Okay, and that limits the representation power of the embedding-based method, because we are losing a lot of information by compressing the input. Okay, and what we wanted to show in this work is that this is actually not true. So the problem with embedding-based methods is not their representation power. The problem is somewhere else that I'm going to talk about it and give you some solution and show that we can actually achieve a state-of-the-art compared to tree-based methods or sparse linear methods, as we can see in the future. So just an overview again of the embedding-based methods. So we have an input, which is in capital D dimensional space of real numbers. And then we have a label vector of an input corresponding to this input, which we show it denoted by y. And it's like a binary vector, k-dimensional binary vector. Okay? And then the goal of our embedding-based method is to learn this f of phi of x, which goes from the input to this binary space. Okay, so it has two components again. So one is this embedding function, and then the other one is this classifier, which takes the embedded vector and takes it to this binary space that we have. Okay. Now, one thing that we do is that for each label that we have, we also consider the embedded version of that label. So each label, it's in the k-dimensional space, but we embed that label as well to a d-dimensional space, similar to our input that we embedded to the d-dimensional space. As a result, we are going to have a label embedding matrix, okay, which is a matrix in R to d times k. Okay, so we have k labels, and then each of these k labels as a d-dimensional embedding. So that's the reason why our label matrix has this form. Okay, and then the classifier that we chose in here is a simple linear classifier. Okay, so how does it work? It's basically just taking the inner product of the embedding and the embedding of the input and the embedding of the label. Okay, so this this form that I've written it in here just shows the matrix multiplication format. But in reality, it's just like the inner product of the embedding vector of the input and the embedding vector of the label, which gives you just like a single scalar, single number. Now, how do we do this classification then? There are two ways. Okay, so one way is that once we do this inner product in here, if the result is larger than a certain threshold, then we say that, okay, this label corresponds to this input. Okay, and the second approach is called like top M. So once we do this inner product in here, this matrix multiplication, we consider the top M entries, okay, top M labels, and then say that, okay, so this is going to be our M labels corresponding to this input. Okay, so we have a theoretical result. I'm not going to go into the details of it, but basically what it says and what we were able to show was that, so in the limit of infinite expressivity of our embedding map, okay, we have a low-dimensional embedding-based linear classifier, okay, that thresholds at half. Remember this model that I talked about it in here. So we have a low-dimensional embedding-based linear classifier that thresholds at half and has a perfect accuracy. Okay, so this theorem basically says that, okay, if we can have any sort of embedding map, then we can have a perfect classifier, even in large output space, even with 25 million classes. Okay, but what is the problem with this theorem if you want to implement it in practice? The problem is that in reality, we cannot have an infinite expressivity of any embedding map. But at the same time, we know that deep neural networks have excellent capabilities in function approximation. Okay, and so as a result, we can use neural networks to learn this embedding map that we have in here. Okay, and let's see how it works. So this is our input embedding function. Now I use sub W in here, so phi sub W, to show the dependence on the weights of a neural network that we are using. So label embedding matrix is the same as before. And now we have a scoring function, which is the linear classifier that we had. Okay, the matrix multiplication between basically the embeddings and the label embedding matrix. Okay, so you can see it in here. So we have this input query, we have this label, we embed them into a d-dimensional space, and then we take a dot product, and this is going to give us a single scalar, which is going to tell us how strong this label is related to this input. Okay. Now, any learning problem, we need a loss function to optimize over it. The loss function that we use in here is actually the margin loss. So what is margin loss? So suppose that we have x and y. X is our input, y is our label. So what happens is that we define this set L sub y, which basically is a set of all related labels for this specific y label that we have. Okay. Now, what does this margin loss function tell us? It says that the scoring function output for related labels, you see, like this is the summation. We have two summations here. So one is summation over y in Ly and summation over y prime not in Ly. Okay, summation over related labels and summation over not related labels. Okay, so the margin loss is saying that the scoring function output for the related labels, hx sub y, should at least have the distance of c from the output of the scoring function for not related labels. This is called the margin loss. It's pretty much widespread for the classification problems, and specifically good for these large output space problems. Okay, so then this would be our algorithm. So let's go over it one more time. So this is our data set. So we have this feature embedding model. It's like a neural network, basically. We have this label embedding matrix. We have this loss function. It's a margin loss. I just described it. We have learning rates. So we initialize our weights and this label embedding matrix in here. And we repeat this process until convergence. So what is the process? We sample a batch of examples. We sample indices uniformly from non-zero indices of y1 to yb. So the point is that this loss function is computationally expensive. So we do this sampling to reduce the computational cost of it. Okay? And then we compute the loss, as I just described, for every batch. And then we compute the gradients with backpropagation. Okay? And then we update the weights and the label embedding matrix here. And we repeat this until convergence. So here's an example. This is like a public data set. It's called like Amazon Cat. It's a standard data set for this large output space classification. You can see that the training has achieved perfect accuracy in here. But there is a problem. So test accuracy has gone up, but gone down. So we have an overfitting. Okay? So in the rest of talk, I'm going to talk about like how can we solve this overfitting problem right now. Any question? Okay, so one standard way that I'm sure all of you know about it for this overfitting problem is to add a regularization term. Okay, so what are the regularization terms that are suitable for this specific problem that we have? So we are going to add two regularization terms, and I'm going to talk about them in detail. The first one is a spread out regularization. Okay, so we can write it mathematically as 1 over k squared summation of y from 1 to k, y prime from 1 to k, v sub y transpose vy prime squared. Okay, so what does it do? So v sub y and v sub y prime are label embeddings for two different labels, y and y prime. Okay, before I continue, I have to mention that we normalize all the label embeddings such that their 2 norm is equal to 1. Okay, so when the 2 norm is equal to 1, it means that all the label embeddings are located on the surface of a hypersphere. Do you have a question?
How did you compute the label embeddings?
Sorry, what was the question?
How did you compute label embeddings?
Okay, so in this algorithm, we initialize it, and then we learn it as I mentioned in here. Yeah.
One other question. So for the test set, when you don't have the label available, or during the inference time, how do you kind of come up with the embedding for a label during the inference?
During the inference, we calculate the label. We actually we use this label embedding matrix because we know like what are the set of possible labels. And then we use this model in here that I talked about it. We calculate this inner product. And then we use some method like precision at k to see how well we are doing. So I'm going to talk about it in the next few slides.
Just to clarify, so you learned the label embedding matrix in the algorithm. Where did the feature embedding model come from?
This is coming from here for the input embedding.
You already had, or you're not learning that, right?
So like there are two separate things. One is label embedding matrix, and one is feature embedding model. Feature embedding model is just used for the queries, not for the labels.
Okay.
Label embedding matrix is something different, but we're also like learning it as well.
Okay.
But we don't use any neural network to learn that.
So it's not a neural net, right?
No, but you can have a separate neural network to learn the label embedding matrix as well.
Okay.
Yeah. Okay, so since we normalize all the label embeddings, what happens is that all of these label embeddings are going to lie on the surface of a hypersphere. So there are going to be in d-dimensional, like in a d-dimensional space. I cannot go over 3-dimensional space, so I just put an example of a 3-dimensional sphere in here. So what this regularization do is that if you take a look at in here, You can see that all these label embeddings are pretty much close to each other. Okay, so intuitively what's going to happen is that when these label embeddings are close to each other, it's more difficult to recognize them and to like distinguish between them. Okay.
The multi-coloring where you have less information.
Yeah, similar to that. Okay. So what will happen if these two label embeddings are pretty much close to each other? Then the inner product of them is going to be close to 1. And then when this is close to 1, this loss function is going to increase. The regularization loss that we have is going to increase. Okay, so instead, what we are going to do is that we add this loss function to encourage the label embeddings to be far apart from each other. Okay, to be widespread over all the space that we have in the surface of the hypersphere. And as a result, the inner product is going to be close to 0. Okay, and you can see that what happens is that this loss function, if you have this case, if you have a spread out embeddings, then this loss function, this spread out loss function is going to be small. Okay, but this is not enough, and the reason is that it over-penalizes correlated labels as well. So suppose that we have 3 examples. One is airplane, one is banana, and one is apple. Okay, so if you want to embed these 3 labels, we know that both banana and apple are fruits, but airplane is not related to them. So if you force all the embeddings of these 3 labels to have inner product close to 0, then this is not a fair classification. This is not a fair label embedding process. And because of that, we introduced this second regularization loss that we have in here, which we call it like Laplacian-based regularizer. So what does it do? If you have banana and orange, so in the right side, you see that they're spread out, but they're over-penalized. Because both of them are fruits, we want both of them to be pretty much close to each other. And on the left side, you see that they're not over-penalized. So they have a pretty much good distance from each other. So mathematically, we can write this as 1 over k squared summation over y from 1 to k, y prime from 1 to k, the norm to a squared of y sub v sub y minus v sub y prime times u sub y prime. Okay, so this means that if these two are, u here shows a measure of similarity between y and y prime. So if this similarity is high, then we need this term to be small such that the loss function doesn't get large and go down to 0. Okay. So now the question is that how can we figure out this u sub y prime? What is a good measure of similarity? Let's go over the glass regularization. We call it graph Laplacian and spread out regularization. So we have a spread out regularization. I showed it as this form mathematically. We had Laplacian-based regularization. I showed it at this form. And then the glass regularization that we have in this work is the summation of these two. That if you simplify it mathematically, it's going to be something like 1 over k squared v transpose v minus u, the Frobenius norm of it squared. Okay. Now, how do we choose this u matrix, which is pretty much closely related to this u sub y prime? We take a look at the graph that we have for the labels and the items. Okay. So item is the input query, and the labels are the labels. So, consider these two labels, I and j. You can see that the items that they are connected to are pretty much the same as each other. Okay, and this gives us some good measure that, okay, these two labels are pretty much correlated with each other. Okay. Now, we use this intuition to define the matrix U. So if the label matrix is Y, which is like an n times k matrix, binary matrix, then the co-occurrence matrix would be Y transpose Y. So the I and jth entry of this co-occurrence matrix shows that how many times I and j have happened to with each other at the same time. So here, for this graph, it would be 2. Okay, because for 2 items, they have co-occurred. Now, if we define this degree matrix Z which is a diagonal matrix in it has k columns and k rows. Then we have this conditional frequency, which is number of times that y and y prime have co-occurred, divided by the number of times that y prime has occurred. Okay, and then we have this conditional frequency added into this glass regularization, and this would be the final form of the glass regularization that we have. It's basically the average of the conditional frequency for y and y prime, as you can see, which is a measure of showing how much these two labels are basically related to each other. Okay. So these are the public data sets. Like if you take a look at the papers in classification with large output space, these are the benchmarks that people test their methods on. You can see that they're mostly related to like Wikipedia or Amazon reviews. So feature dimensionality, label dimensionality, you can see that, for example, Amazon 670K, it has 670K labels. Here are the number of training points, number of test points, average points per label, and average labels per point. So you can see that these are challenging problems. For example, for Amazon 670K, the number of training points is less than the number of labels that we have. So it's really a challenging problem to solve. So here is some hyperparameter tuning. I go over it quickly because we are running out of time. So for the choice of regularizer, I talked about the spread out. If we only have a spread out, you see that our method outperforms it. If we don't have any regularization, you see that this is the difference between our work and the non-regularized model. And then gravity is a previous work by Google published at iClear last year. For regularization weight, you can see that it shouldn't be too large or too small. So lambda equals to 10. Dropout in the neural network is a very good regularization technique. You can see that like a moderate dropout helps. Batch size, larger the better. Embedding size, again, the larger embedding size, the better performance. And of course, for embedding type, we can have a linear embedding or a nonlinear embedding, but nonlinear embedding with ReLU activation actually helps us a lot. Okay. And finally, two more results that I'm going to present. So one is this generalization gap. So before and after adding this regularization, you can see that this dashed line corresponds to the time that we don't have any regularization. You can see that this is the training and this is the test. But when we add the regularization, what happens is that test accuracy increases and training accuracy decreases. And this is what is expected. Okay, so we have closed this generalization gap from 6.89 to 4.56 and from 53 to 49. Okay. And this is the precision at K compared to other baselines and state-of-the-art methods. We have determined two approaches. One is this embedding-based approach. One is this other methods, tree-based or like one versus all methods. You can see that on 3 data sets, Amazon Cat 13K, VKLSHTC, and Amazon 670K, we outperform all the baselines. And in several other data sets, we either outperformed just the embedding-based methods, and in Delicious 200K, we do not outperform the Slick, which is also an embedding-based method. Okay, so just to conclude, just 3 takeaway messages. One is that embedding-based methods can have competitive performance compared to other approaches, like tree-based methods or these sparse methods for large output space. The other takeaway message is that neural network can suffer from overfitting, so having a good regularization technique, which is tailored specifically for your classification problem, is going to help a lot. And the third is that, data augmentation technique, regularization techniques always helps us for reducing the overfitting problem. Thank you so much for it.